Today I'm going to talk about some of the work we are doing in Newcastle Urban Observatory, which is UK's one of the largest and most diverse IoT test bed, and see how we collect data and what kind of application we are working on those, what kind of smart city application we are developing using that data, and while doing that, what are the research challenges that we are trying to solve. So I'm going to highlight those things as part of this talk. So that brings me to the title of today's presentation, which is New Horizons in IoT Workflows Provisioning in Edge and Cloud Data Center, using the osmotic computing approach that we invented at Newcastle along with collaborators from Cardiff University, TU Wien, and Swinburne University, Australia. So I'm going to give you a detail on all these concepts as part of today's talk. So this will be my outline for today. So first, I will give a brief intro to IoT landscape, then I will look into the application context of IoT, and then the interlink concept of how IoT and big data are related. They're not separate things. And then we will look into how we as a distributed system researchers can do in this complex ecosystem IoT application and big data science context, and then what kind of new computing research we can do in this new distributed system scenario. So I will be talking about that. And to that end, I will be talking about the research challenges that we are solving in that context. So I think as most of you are distributed system researchers, so we know that the next trend for our community is Internet of Things, big data, and using both of them to enable smart application. And those smart application, as you see in this slide, that spans across multiple disciplines now. So as you see, if you see from the right-hand side, it goes all the way from smart grids, mining, industry 4.0, smart agriculture, smart transport, connected cars, healthcare, smart home. So you name it, every domain are now using IoT sensors and actuators to make their discipline more smarter, automated, and maybe to some extent autonomic. So that's the whole idea of using IoT system to make the system autonomic, self-healing, similar to how human body or any organism body works. So that's the key enabler of IoT is to make this physical environment, which used to be manually and managed in a static way. How can we manage them in autonomic and intelligent way through intelligent IoT sensing and actuation? So this is the broad overview of like what I'm to say here is the IoT is now being used or being trialed across different disciplines. And that brings me to, okay, so all these smart meters, so water management, smart grids, smart agriculture, they are the application domains. However, they are just where we want to make impact, but the real research for us, for the computing discipline, that lies on the right-hand side, as you see here. To really enable IoT application, we need to bring across multiple distributed computing paradigms, right from edge computing, software-defined networking, cloud computing, and virtualization and software as a service. All those things need to come together in different shapes and sizes if we want to enable application across any of those disciplines. And it's very complicated. It's quite complicated than what we used to work in early 2000 about hosting a web application in the cloud data center. That is a very simplistic case of distributed computing application. But if you want to move into the smart IoT applications where you have real-time sensing and actuation, those simple application deployment models which was supported in early 2000 when the cloud computing just evolved in 2005 are not going to work. For example, we cannot take a Hadoop or Apache MapReduce programming model and say we can enable whole IoT application. It's not going to do that. Obviously, something like Apache Hadoop or MapReduce will be one of the small component of IoT application, but on its own, it cannot solve the whole IoT application management challenge that I will discuss in my today's presentation. So obviously, as I said, IoT and big data, they are interrelated concepts. They are interdependent. So the current prediction from IDC says that most of the big data in the next 5 years will be IoT will be one of the biggest contributor to the big data landscape over the next 5 to 10 years. Of course, this prediction goes till 2025, but we can extrapolate that to 2030, 2035. So as more and more disciplines adopt IoT solutions, we will produce more and more big data. And as you see, by 2025, the prediction is saying IoT related applications are going to generate 160 zettabyte of data. And that's too much data. Even if we want to, we are going to provision all the public and private cloud data centers that we have available from Microsoft or Amazon or anybody else, we are not going to be able to store all this data. So what that means is we need to find new data management and resource management algorithms that can do real-time decisions based on this data and then just throw the data, because we can't sit on the data like before. We just need to use the data for our decision making and then move on. And for that to happen, we need new algorithms and new research to enable that thing, because we are going to have a lot of data as you see from this prediction. So this is that was one prediction, but however, at Newcastle, as we run our own test bed that we call as Newcastle Urban Observatory. So some of the numbers I show on this slide can tell you that how big is this big data. And this data that I'm showing here is just for Newcastle IoT test bed. It doesn't include any other cities or any other towns or councils in UK, just for our Newcastle area. And as you see from this one, we have deployed across the Newcastle almost more than 3,000 types of sensors. And as of now, we have more than 1 billion data points. And every minute we produce 2,000 data points from those deployed sensors. And it's growing and growing by the day as we deploy more and more sensors. And if we increase the data sampling frequency of the sensors, the number of observation per minute is going to increase as well. And in our test bed, we collect almost 64 plus variables of data across different application patterns like weather, traffic, water flow, water quality, people flows, air quality, energy consumption, smart building, you name it, we collect all those data. We also work with Newcastle City Council, and we have deployed more than 250 kind of CCTV cameras across the city to monitor the traffic, and from there we get millions of images. So what we are trying to say here is, okay, so big data is just, for IoT is not a hype. We have a real world example at Newcastle that says that actually big data for IoT is a real problem. And then we need solutions to solve it. And this numbers actually shows you that example that even for one city, which is instrumented with IoT sensors, you will end up with a lot of data. And we need new solutions to be able to process those data in real time so that we are not being required to store the data for a lot of time, because we are not going to be able to do that. Obviously, at Newcastle University, we use this data for many kind of application, from smart city traffic planning to energy management to building management to flood and disaster management to air quality monitoring management. So our School of Civil Engineering, as Professor Zoom might know, is very, very strong in environmental hazards, environmental monitoring in urban environment. So we as a competing school, we work with School of Environmental Science and School of Civil Engineering and enable different kind of application in flood management, landslide, air quality, using this urban observatory data that we showed you. So now our challenge is, what kind of distributed computing infrastructure we can build for this environmental science or civil urban infrastructure researchers, so that they're able to use this data in real time for different kinds of applications, such as flood management or landslide management or air quality management. So we take that as the motivation to motivate our next generation distributed computing research. Right, so this is just one of the example. We use urban observatory, CCTV image, we use social media data to detect real-time flash flood in Newcastle city center. For example, this is one of the tunnel in Newcastle city center, and this happened in, I think, 2013, when we had a flash flood in Newcastle, where the tunnel got flooded and people were not made aware of this flash flood, and as you see, a lot of people were stuck in that flood. So we are developing solution based on monitoring the CCTV images and the water level sensor and social media feeds to be able to detect this flash flood before it happens, and then send warning signs to the drivers in that area. So this is one of the application which is funded by, one of the project funded by National Environmental Research Council of UKRI Research Council, where we are looking to use urban observatory data to develop real-time flood modeling system. This is just one of those examples. Right, so that was the application context, but of course we are computer science researcher, we need some computer science motivation, why we want to do this new kind of research. So traditionally, around 2013, 2014, when this IoT came into existence, most of the IoT data processing paradigm were cloud-centric. So what I mean by cloud-centric is those IoT data processing paradigms such as Amazon AWS IoT, Azure IoT, Google Cloud IoT that you see on the right-hand side, they required all the IoT sensors to send all the data in real time to the centralized cloud data center. So obviously that's okay when you have few sensors like 10, 20, 30, 100, but that's not okay when every city is having thousands of sensors. Just imagine every city sending millions of data points every minute to this centralized cloud data center. So there are many problems with that. The first problem is wasting of bandwidth. So the issue is you do not need all the data all the time. So there's no point having a computing paradigm where you have to send everything to the cloud all the time. So that's leads to waste of bandwidth. And second problem is high latency. So based on the network uncertainties and network protocol, you can have variable level of latencies with IoT data. And why that is a problem, I will be covering in my later slides. Why IoT networking is challenging, and we need some way to manage it. It's not the best effort. It's not, you cannot ensure that IoT network always give you good latency or constant latencies. It always changes because of the mix of IoT protocols and networking architecture, which is implemented by different IoT systems. So this paradigm, which was supported by these big companies, didn't work, doesn't work for real world IoT applications. So having that as the motivation, we wanted to invent a new IoT programming paradigm that can bring across disparate level of distributed systems. So you see in this picture, this shows this holistic system level architecture of IoT infrastructure. You see in this layer, there are three layers. The bottommost is IoT layer, the middle layer is the edge layer, and the upper layer is the cloud layer. As we all are distributed computing researchers, we all know that each of these layers are on its own a very complex distributed system. Each of them, like a cloud computing layer, is a complex distributed system. We have done a lot of work on that, on resource allocation, security, other things. Similarly, the edge layer is also a very complicated distributed system where you have different kind of edge devices, gateways, mobile phones that collect data, and then you have the IoT layer where you actually deploy small scale tiny devices to sense data about environments, building, or smart cars, anything. So if going a bit more in detail of this picture, so at the bottommost layer you have the IoT layer where you deploy restricted small scale sensors and actuators which has limited storage. So at this layer you can only collect the data, but you can't really do too much processing because they are very restricted in terms of computational and storage power. So mostly this IoT layer is connected to the edge layer where you are able to do some pre-processing, but as compared to the IoT layer, it has more storage and more computing power. But again, the edge layer is not also very advanced. So ultimately, when you have a lot of data streaming from hundreds of sensors, you can't store that at the edge layer, you have to push that to the cloud layer. So then, however, the hard part here is whatever IoT programming paradigm we develop, it needs to work across these three layers. So most of the research available in application orchestration in cloud computing, they only deal with cloud layer. They don't deal with edge and IoT layer in terms of orchestration of data and the resources. So that brings up motivation that we need some kind of new IoT paradigm that can bring all these three layers together and still make sure that the data that we need is always available across the analytics engine that could be deployed either at the edge layer or the cloud layer. So to solve that problem, in 2016, we came up with this new IoT programming paradigm based on microservices, which we call as osmotic computing. which was published in IEEE Cloud Computing Magazine 2016. So pretty much, osmotic computing is a new paradigm to support efficient execution of IoT application between cloud, data center, and the edge network. And the fundamental principle behind osmotic computing are the microservices. So you decompose your complex IoT application as a collection of multiple microservices. So I will now go in detail of this osmotic computing paradigm and see what are the main building blocks of osmotic computing paradigm and how we can use that to solve IoT data management and resource management challenges. And that gives us a baseline to develop our research around these IoT applications. So just to give you an overview of osmotic computing, so what motivated us, this name osmotic computing, was this process in chemistry called osmosis, which represents the seamless diffusion of molecules from a concentration, high concentration to lower concentration. So we use this philosophy to think that why can't we use the same osmotic principles in context of IoT services, where the microservices can move between cloud, edge, and the IoT layers based on the data processing needs, based on the security needs, based on the privacy needs. So we took the same osmosis principles and applied to this computing discipline, where the molecules are represented by microservices, and the concentration is represented by cloud and edge data center, which are different parts of the system. And then you move those microservices across those layers based on your deployment need, networking need, security need, QoS need, and you name it, based on whatever parameter you want to optimize as part of your application. So putting all this thing together, so we came up with this something called osmotic computing paradigm that actually glues together this IoT layer, cloud layer, and edge layer. But of course, this is conceptual one. Now we need to look into what kind of research we need to do to actually enable this vision of osmotic computing. So I will go into that. So as you see that osmotic computing gives you a federated view, where on the outside you have these IoT devices, sensors, and actuator. In the center, you have the edge data centers like small scale gateways and mobile devices. And in the center, you have those traditional cloud, private cloud, public cloud. And somehow the osmotic computing has to seamlessly manage data and computation across all these three layers, which is very challenging. It's very challenging because all those three layers are very heterogeneous in terms of computational power, networking, and software architecture. So it becomes really challenging to manage data and resources in such complicated ecosystem of. So in a way, you can say it's a distributed systems of systems, and it becomes very challenging to manage data and application and resources across those layers. So because everyone knows the backgrounds, I will not deal too much into this. So the first building block is obviously sensors. That is the IoT layer, where we sense data about our environment. We collect this data. Then the second building block of the IoT is the connectivity, as I said. And why connectivity is important? Because connectivity is important because we want to collect real-time data from IoT sensors. As you see from this picture, we have so many different kinds of IoT protocols at each layer of IoT system. So there's a different protocol that you use between IoT and the edge layer. There's a different protocol used between edge and the cloud layer. And then each of those protocols have different latencies, different throughput, different delay, and different energy profile. And each of those combination that you're using in your application will decide your data latency or age of data. So that's why it's very hard to control the network QoS in IoT system because of this IoT protocol and network uncertainty that you see in this picture. And as I said, in the middle layer, you have this edge computing devices, which are like small scale computer like Raspberry Pi, a mobile phone, where you can collect data from, for example, in this picture, you have the smartwatch. This could be a temperature sensor or a building sensor. It could be even a small autonomous cars. And at this layer, you can do pre-processing of the data before you pass it to the cloud for to some kind of big AI engine to do some decision making. But what we need to take away at this layer, that at edge computing layer, you are having different kinds of hardware devices, right? From Raspberry Pi to video board to mobile phone. And this heterogeneity makes it very hard to optimize the performance of data analysis application, because each of them will perform in a different way at different type of hardware devices. So why edge computing is good? Edge computing is good because it can give you improved response time. It can improve interoperability between legacy and modern devices. So this is important in context of Industry 4 application, where you know your old manufacturing devices, they don't really speak IoT protocol. So then you can use this edge computing layer to network the old PLC devices of those machines with the IoT layer. So that's where the edge computing comes into picture in terms of improving the interoperability in the Industry 4 domain. And obviously, if you have some sensitive data, then you don't need to pass it to the cloud. You can do processing on the edge itself. So it will improve data security and compliance. And obviously, we all know at the end of it, if we want to run a big AI algorithm on our data, we need some cloud infrastructure. So which we all are very aware. It's a rack of servers with thousands of servers. You just push your data there, run some big data engine to process your data. So right, so that was things. So the main fundamental of osmotic computing is based on microservices. So microservices is a new way to virtualize your application. So why microservices for osmotic computing? Because it's much more lightweight than virtual machine. So as you see in this picture, unlike virtual machine, the microservice itself doesn't have a copy of operating system. Because they don't have a copy of operating system, they are much more lightweight than the virtual machine. And since they're lightweight, that means we can run them on small scale edge devices, which is not so feasible with the VM based machine, because each VM has its own operating system. So the code base is quite big. And since they are very lightweight, it's also very easy to migrate the microservices across the edge and cloud network. By migration, I don't mean doing the live migration. By migration, I mean, you know, snapshotting the data and then moving the data, and then you can start either edge specific microservice or cloud specific microservice to process your data. So as you just in terms of technical terms, if you want to migrate a Docker container, which is one of the way to migrate microservice, there are some very simple commands that can help you snapshot your data and move your data to edge layer or the cloud layer. They can restart your microservice. So from programming point of view, it's quite easy if you program your IoT application as a Docker microservice or Docker container, because it gives you all the interface to snapshot and migrate it. So in terms of programming, it's not a hard challenge. Of course, coming with the algorithm on when to migrate in response to QoS and security needs, that's the hard problem. But in terms of actually coding something like migration is not very difficult, because a framework like Docker already provides you that feature, as I show in this slide. So right, so as I said, so osmotic computing is a mixture of edge computing, IoT sensors, actuator, cloud computing, and microservices. So obviously we bring this together, we get this osmotic computing infrastructure. So that's just the infrastructure. Now the next challenge is, how do we represent and deploy IoT application on this infrastructure? That's the next challenge. So moving on to that. So at Newcastle, we have developed this concept of IoT graph, which you can use to represent your IoT application in any discipline, either in healthcare or smart city, flood management, landslide, air quality. So what this graph defines? This graph defines, this osmotic IoT application graph says that an IoT application can be described as a directed acyclic graph of microservices, where at each layer you have different types of microservices which have control and data flow dependencies, and each of those microservices have different hardware, software, and networking requirements. And as you see in this picture, you see there are three different colors: blue, red, and yellow. That basically means that if you want to deploy an IoT data analysis task at the cloud layer, you need a different kind of microservice as compared to the edge microservice and IoT microservice. Why they're different color? Those different color doesn't mean that they're not using same virtualization. They may use the same Docker kind of engine to create these microservices, but they are of different color because they might have different hardware and software configuration, which is controlled by your underlying infrastructure. For example, if your edge device has very inferior hardware configuration, then you can't just take a cloud microservice and run it there. You need to adapt your microservice for the edge layer. That's why they are of different colors. So you have to. So what you have to do is, first you have to decompose your complex application as a collection of microservices come up with your DAG graph, and then describe your control and data flow before you can deploy that on the Osmotic infrastructure. So just imagine that we came up with such a graph and you deploy that on Osmotic computing model, you will end up something like that. You will end up with a collection of microservices at different parts of your Osmotic computing, edge layer, cloud layer, and then you end up with some networking. So then after you deploy it, of course, you need to collect data from each of those microservices. So you need to implement a lot of networking layer to be able to make those graph work together, which is very challenging, that I will show in the next slide. So even this if you get one of this networking wrong, you will end up with the wrong decision. So all those distributed computing researchers who used to look into the failure management, fault management, this gives a even more challenging scenario to look into that. So here, just failure of microservice is not the only problem. Failure of networking link can also bring down the application, which is much more tough because each of those layers use different kind of networking protocols, as I showed on a different slide. So we have to manage the failure of network links along with the microservices, along with the IoT sensors. So this really complicates our problem. So imagine that you come up with this complex IoT application graph, which will look like this collection of microservices. Now, the hard challenge is, how do I distribute my microservices across different layers of my Osmotic computing infrastructure? So, and why it is hard? It is hard because your search space in terms of hardware, software configuration, and your QoS optimization function is very hard and very. So we need to look into. So we need to look into new kind of mapping algorithms that can take hardware and software requirements of these microservices and then find the optimal deployment. So now, before I go into those Osmotic challenges, I just want to highlight that at Newcastle University we have developed something called abstract IoT data analysis patterns. So, for example, if you want to create a flood modeling application or air quality modeling application, you as a researcher, say you're from civil engineering, you need to know what kind of data analysis patterns I need to create my application. That's the first question. So I need data capture, I need data store, data inference, data filter, data aggregate. So what we did, we interviewed the different domain experts from healthcare, smart cities, Industry 4, and we come up with what are the different data analysis patterns they need to deal with in their IoT application. We captured that requirement, and from that requirement, we came up with abstract data analysis patterns and abstract data flow patterns. So data analysis patterns means that what operation you're doing on the data, and data flow pattern means how data is transmitted across the layers. So as you see in this one, data flow pattern includes edge to edge, edge to cloud, cloud to cloud, cloud to edge. And we then validated our data analysis patterns and flow patterns across different kind of application. If you want to know more about that, you can refer to the paper given in the below in the slide, and that gives all the details about that. So for example, we validated our data analysis patterns in context of air quality modeling project, which is funded by Research England at Newcastle University. So for example, the workflow for air quality modeling includes you collect data from CCTV and sensor, then you use filter, convert data, remove anomalies from the data, then you use some kind of image processing model, then you use air quality model, and then you visualize your results. So these are the human readable analytics you want to do in air quality modeling. Then we converted, and we can capture those using our abstract patterns, like CCTV can be mapped as a data capture, filter convert can be mapped as data aggregate, data filter, data translate, data inferencing, and air quality model can map the data inferencing. So then once you capture the abstract pattern, then the next point for you is to convert those into cloud, edge, and IoT microservice and bring it together. Similarly, we have validated our abstract data patterns for flood modeling workflow as well, as you see in this picture. And you can use our patterns to create as many different kinds of smart IoT application that you want. Obviously, when you develop this kind of pattern, you want to do certain user study and say whether these patterns capture the requirements, as you see in this picture on the right-hand side. Most of the domain experts with whom we validated our data flow patterns, more than 80% of them agree or strongly agree that our data analysis patterns and the data flow patterns capture their requirements. So we believe that the data analysis pattern that we developed is quite generic and it would be used across different IoT application disciplines. Right, so that was in terms of IoT application graph composition related research challenges. Now, coming to more traditional distributed computing research issues, one of the hard challenges, how do we characterize the performance of microservices? For example, if I'm to deploy a microservice at the edge layer, at the cloud layer, or the IoT layer, how do I do the performance characterization? And why, as compared to traditional distributed benchmarking research, why this is hard? This is hard because each of those layers, IoT layer, cloud layer, have different performance goals. If you see in this slide, so the network stability, throughput, optimality, routing delays, fairness in network resource sharing are some of the important parameters for the edge and the cloud layer. So if I'm going to deploy my microservices on edge and cloud layer, I need to benchmark my microservice for this parameter. Similarly, if I'm going to deploy my microservice on the cloud layer, I need to benchmark it for response time, platform scalability, reliability, virtual service utilization. And based on how many microservices are part of your application graph, you have to do that for each of them. So as you see, it becomes more and more challenging if you really want to optimize your microservice deployment on this three-layered IoT infrastructure that we call osmotic computing. And each of those, you have to repeat and calibrate the performance of those microservices. And then it's also dependent on what kind of computation you are doing inside the microservice. If you're doing simple aggregation and statistics, perhaps they're easy to benchmark. But if you're doing some machine learning or AI technique inside the microservice, then that's harder to benchmark. So it just increases your complexity more and more. So going back to literature, of course, literature has certain benchmarks that you can use. For example, you can use TPCX IoT to benchmark data aggregation pattern on the edge layer, or you can use Google ROADDEV for linear load kernel for benchmarking stream processing queries. But what is the problem? The problem is these benchmarks only represent performance of a specific kind of IoT workload, like stream processing or database workload. They don't represent the behavior of IoT graph, which can include a combination of those. So then what is the solution? The solution is we need to identify and collect this kind of different suitable benchmarks. We need to connect them either hierarchically or logically, and run them together to generate a real-time conclusion about performance of our IoT graph across the three layers. So we have a project ongoing with that. However, doing real-time benchmarking on real infrastructure is hard because of many reasons. Those reasons includes how do you replicate different kinds of IoT protocols like Wi-Fi, 4G, Bluetooth while benchmarking? How do you scale your benchmarking experiments to thousands of devices or thousands of servers? That's also very hard in real infrastructure. So obviously you can do real-time, real infrastructure-based performance characterization. It's not impossible, but it's very hard, and it's very hard to generalize. For example, no one will give you access to the IoT testbed to do this characterization. For example, at Newcastle Urban Observatory, we provide people with our data, but we don't give them our hardware to run their experiments because it's our production environment and we cannot just lease that to students or researchers to benchmarking. So it becomes a problem if you want to use real infrastructure for your benchmarking. To solve that problem at Newcastle University, we are looking at a project called IoT Sim. So what we are doing in this project is we are developing a collection of discrete event simulator where each event in IoT, each activity in IoT system model as a discrete event. And then you can combine these simulators together to model your osmotic computing algorithms or your data management or networking algorithms. For example, in this picture, we show that you can include IoT Sim Edge to model the edge layer of your edge and IoT layer of your IoT application. You can use Big Data Sim SDN to model the SDN networking between your microservices. You can use IoT Stream to model real-time computation of IoT data. So you can pretty much glue together multiple kinds of simulators, and then you can validate the performance of your IoT graph under different networking scenarios, different hardware scenarios, different software scenarios. We have released the software code of some of this simulator you can find at this link. You can download and start testing the performance of your algorithm as part of this discrete event simulator. So by using this discrete event simulator, you have two advantages. For example, you can scale your IoT infrastructure to millions of devices or millions of servers, which is quite not possible with real infrastructure. And secondly, because we are using simulator, you can reconfigure your IoT network with different protocols. You can use Bluetooth, Wi-Fi, 4G, and you can change those configuration in the matter of minutes and seconds. So you don't have to set up those things manually, which can take weeks or months, even for small scale infrastructure. So this is one of the big research project we are doing at Newcastle. We have released the code base few months ago. So you're happy to go to this link, download and try it out. And if you have any problem, we are happy to talk and help with your research, how to use this tool to validate your IoT algorithms. The second challenges that we're working at Newcastle is about how do we optimize the deployment of microservices across different layers. Why this is hard? As we have all worked on cloud computing, any mapping problem is NP hard. Why it is NP hard? Because we have a lot of options and we need to select a few based on our constraints. And why it becomes harder in case of IoT? It becomes harder in case of IoT because we have 3-layer system: an IoT layer, edge layer, and cloud layer, and each layer has its own constraint. For example, at the IoT layer, we want to save the life of the battery of the IoT devices. At the networking layer, we want to save the network bandwidth. At the cloud layer, we want to save the cost of hosting our AI engine or cost of storing our data. So when you formulate those things in an optimization framework, you will end up with a lot of conflicted optimization function. And as your search space is very high, it becomes really infeasible to solve this optimization problem in real time. So we need to come up with new multi-level heuristic to solve it. And one of the approach which has been investigated in literature is about distributed optimization, where you have optimizer at different layers of the system, and they do local optimization for the IoT layer, edge layer, and the cloud layer, and then they use federated learning to combine the global decisions. So this way, you can speed up your optimization. So this is one of the trend in our community, looking at how do we optimize the deployment and how do we make decisions faster as compared to what we have done before. So as I said before, the whole value of IoT lies in the data, right? How fresh is your data? How new is your data? Because if your data is old, doesn't matter how expensive is your test bed, your result means nothing. For example, in the flood modeling, if I have the data from my sensor which is 1 hour old, then it might happen that the flood has already happened and I'm just modeling something based on stale or old data. So in this case, so age of information becomes a critical factor for IoT application. And the age of information defined as the data freshness. How fresh is the data? And this data freshness is the function of the two network US metrics, including throughput and delay. So these are the two metrics that combined together gives you the data freshness. And at the same time, you are hoping that your system is cyber security secure, no one has hacked it. Otherwise, someone can just replay the stale old data and then you will not realize. So the age information becomes a critical issue in context of IoT application. Why ensuring age information IoT is hard? You can see from this picture why this is hard. This is hard because you have different kinds of networking system across different layers of a system, and each of them have different latencies, different throughput, different energy requirements, and then your data can become slow at any of these layers. So right now, we don't have any methodology that can make sure that, okay, I want to ensure for my IoT infrastructure, my age information is less than, say, 10 milliseconds. We don't have any such solution available. But we need such solution if we want to make this real-time decision-making application really feasible for our future application. It's a hard issue. Your age of information can be affected by many other factors. That includes device dynamics. For example, the battery life failure of your IoT device, the software failure of your edge device, the hardware failure of your networking device, the link failure, the network can get congested. For example, if you don't provision your IoT network and devices in optimal way, you might end up overloading your network connection and your edge information will degrade. So you need a lot of complicated network provisioning algorithms to make sure that you preserve the edge of information, which is critical to your IoT application. This is other area of research that we are working on with Leeds University with Professor Zhu, and we are working on a paper on this topic that we work in collaborative way, and we believe this is a very important problem to solve in context of IoT application and the age of data. So that was the networking perspective, but when you put all this thing microservices together, which are doing different IoT data analysis, they are collecting data from different IoT sensors and actuators. But the issue is, since the distributed systems, things will fail. Your microservice will fail, your network will fail, or your sensor will run out of battery power, and many things will go wrong. Then the hard question for us is, in this kind of complicated systems, how do we find the problem? How do we debug the problem? That's a very critical issue. And debugging the systems, osmotic covered infrastructure is not easy, because you have a large failure surface, right, from IoT layer, edge layer, and the cloud layer, right at the software layer, hardware layer, and networking layer. Things can go wrong at any of those layers. So the question for us is, how do you monitor and debug IoT application in real time? So this is an unsolved problem, and people have started looking into that. And some of the approaches they are looking is based on chaos engineering from Netflix, where you actually deliberately fail your infrastructure, learn different failure patterns, and then you train your AI to be able to detect those patterns at runtime. So there are different methodologies people are looking in terms of how we can automate the failure debugging of IoT infrastructure. Very hard and new problem, but no solution there. So we need to work on that and figure out a way to solve it. And obviously, as you see, there's a big IoT system. If we are going to collect the monitoring data about each part of the system, it's quite likely that we will end up with a big data problem in terms of monitoring itself. We are collecting so much big data about the current status of your IoT device, edge device, cloud device. You have a big data problem in monitoring itself. Forget about your application layer. So we need to find some optimal solution at the debugging layer to minimize the amount of data we collect about devices. Otherwise, you will have two kinds of big data. One big data as the application layer that you need for decision, and one big data at the monitoring layer, which you need to fix your system. So we need new techniques to fix that as well, and we can look into AI-based techniques and federated learning to look into to solve that problem as well. Again, no solution exists for those classes of problem. Concept with an example where we develop a monitoring system for a smart parking application and see how we monitor a smart parking application which is distributed across edge, IoT, and the cloud layer. So pretty much this was our application that we implemented, in which our goal was that, okay, if a Newcastle City Council makes a parking somewhere here, we want to put some vacancy sensors, the sensors that can sense whether some parking is available or not. From that, so from that sensor, data is sent to a microservice in the parking that computes which parkings are available, which parkings are not available. Then that information is sent to a parking allocation service or route selection service in the cloud, to which the drivers can connect and figure out which parking in Newcastle are available at that point of time. And then along with that, we have other microservice, which is user management, which manages the account details and payment details of those users. So we have collection of 3 microservices, and we demonstrate how these microservices can be used to automate the smart parking application. And then issue is, how do we make sure that those microservices are performing correctly through a specific monitoring methodology. So our main technical question is how to ubiquitously monitor the QoS of microservices mapped to different parts of osmotic computing environment. That means edge, cloud, and IoT. So in our smart parking application, we had 3 main microservices. This was our setup. So in the C1, both for the user management, both MySQL and Tomcat are in the same container, but for the C2, they have their own containers. In S1, the selection vacancy service run on the cloud, but in S2 they run on the edge device. Okay, and in E1 the parking management service runs on the edge, but both MySQL and Tomcat run the same container. But E2 they run in the two different containers as two different microservices. So here two microservices, but just one microservice, and we use our monitoring technique to monitor the runtime implication of these different deployment decisions. So what I'm trying to get here is your deployment decision can affect your runtime performance. So you need to link those two things together to be able to see how you decompose your application to microservices and how they are going to be hosted, either in same container or different container, and then how that leads to different. Our experimental setup. So on the cloud layer, we had an OpenStack virtual machine in which we hosted Docker engine, which runs MySQL 5.7 with and Docker container with Java 8 and Tomcat 7. On the edge layer, we had Raspberry Pi Model B running Raspbian with one CPU, 700 megahertz, 512 MB RAM, and 4 GB memory. And that has also MySQL 5.7, Tomcat 7. And we use the Apache JMeter to generate the car population. So that emulated the request for parking. So and we varied those requests to understand different car population from 10 requests per second to 500 requests per second, and then see how this different car population leads to different loads on the microservice, and then how it changes the behavior of the edge microservice and cloud microservice, and whether this osmotic monitoring had the capability to capture all the system dynamics or not. So that was the goal of this the user management service, and our observation was that C2, so deploying in the cloud Tomcat and MySQL as a separate container leads to better performance for user management service, as you see from this graph. So C2 had more stable resource utilization across MySQL and Tomcat as compared to when they are in the same container. Because they are in different C group, their resources are isolated, so they never compete for each other. There's no contention. So what could be happening here? This time, both of them are contending for the CPU because they're in the same C group. So that's why nothing is getting done, and they're just wasting time in context switching. Because the Docker cannot context switch them correctly because they are part of the same container. But if for the other ones in their different C group, the resource management is much better, much easier for the Docker. That's why you don't have. So this is very classical thing happens when you deploy your microservices in the cloud. It's not just for the IoT, but any cloud application has this implication. And this kind of behavior you can discover through benchmarking that we learned in cloud computing module. So this is what we want to discover before we deploy application. But even after we discover that after deployment as well, we want to monitor this thing to see if these things are coming up, and then if we encounter this kind of symptoms, then from the monitoring we can change our system configuration and then just separate those microservices. This is how, this is why monitoring is so important. But then again, some of these symptoms can also be discovered through benchmarking as well. If you benchmark them into different scenarios, you can get that. Now this is the second experiment where we had this selection vacancy algorithm running on one in the cloud and one on, sorry, no, this is not selection vacancy. This one is, sorry, E1. So this was the parking management running in the E1 where this running both the Tomcat and MySQL running in the same container, and here they're running in different container, but on the edge. And our observation was E1 has better performance than E2. So here it is contradictory to the cloud. Here what it's saying is on the edge running them together is better than running them separately for the parking management service. What would be a reason for this observation? Because Edge is a small scale device, it doesn't have much load balance resource management to be done by Docker. So in fact, if you try to do that, you're actually wasting more resources in terms of managing different C groups and different resource management policies for different containers. So on for this kind of resource constrained device, even a greedy approach of packing everything together leads to a better performance than trying to optimize in the cloud. So what it is saying is that the resource management policies that you design for cloud may not work as it is for the edge, because the edge has a less power, less computation, so you can't have the same policy there. So you need a differentiated policy for different part of the system. Now, and obviously, if your debugging system can detect some problem in our infrastructure, the next step is how do we fix the problem? How do you heal your system? So some heal, and those fixing could be of many kinds. Either you need to do some kind of auto scaling, or you need to do some kind of replication, or you do some kind of load balancing, or a combination of those two. So then how do we do that at the runtime so that your age of information or age of data doesn't suffer? Again, a very hard problem, and we do not have solution for those for this IoT context. So this is other very interesting topic to work on going forward, and we will be working on that.